Hello, dear children. Today we will try to see electric field intensity, electric field due to a point charge, then electric dipole, then dipole moment. Let's try to see like this for today's class. I will make this video a little bit short so that it will not be a problem while uploading. And if you want to make note also, you can make note from it. Try to keep a separate notebook, and you better try to note down the notes for these topics. Okay, so let's see. Electric field. When I say electric field, it is the space or region surrounding a charged body where the electrostatic force of repulsion or attraction exists when a test charge is brought in it. Okay, now when you play football also, in that football field, not the ground, I mean the football field where the football can be played, if a ball is making a goal, then there is a mark there on the field that if it is kicking from that particular field, then that goal is valid. But if a ball is kicked from outside the field, then that goal will not be a valid goal. Okay, just like that here also for the charge. Okay, it is just like that. So electric field, it is a space. Suppose a charged body, so let me have like this. Suppose if a charged body is somewhere here, so let's take it as Q somewhere here like this, at this point. Okay, I mean a point charge is residing here, and around this charged body, the space or region surrounding this charged body where the force of attraction or repulsion, rather your Coulomb's force of attraction or repulsion exists, then this region surrounding this charged body where the force of attraction or repulsion exists when a test charge is brought in it. Suppose if you bring a test charge, generally when we say test charge, it is a unit positive charge, and it should be a point charge. Point charge in the sense that the charge should be, the size of the charge should be as small as possible. Got it? So that charge, when it is brought somewhere from far away up till somewhere here, say let's take it somewhere here, then no force of attraction or repulsion exists. Why? Because when it is somewhere here, what happened, the field is only up to this boundary, so there will not be no force of attraction between this given charge and the test charge Q naught. Generally test charge is denoted by Q naught. Okay, so this Q naught and Q, there will not be no force of attraction or repulsion. So if that point where there is no force of attraction or repulsion, then what happened, that region is said to be out of the field of this charge. That means this charge. Okay, but when this test charge Q naught is brought somewhere here, generally as it is inside the field, the force of attraction or repulsion will be surely there. So those region or space surrounding this charged body where force of attraction or repulsion exists when such test charge is brought in it. Got it? Yes. Next, say I'm giving you here again another definition. The region or space around a charged body within which its influence can be felt. Suppose if that charge is brought inside its field, naturally its influence means force of attraction or repulsion. Okay, that influence can be felt. Those regions where this force of attraction or repulsion which can be felt, that region is known as the electric field for that particular charge, given charge I mean. So some are given here, some notes are given here, so you just let me read it out. Number one, the charge which produce electric field is known as the source charge. Okay, the unit positive charge brought inside the field to the test electric field to test the electric field or force is called test charge. The charge which is brought to test whether the force is exists or field is existed or not, that charge we call it simply as test charge. Number 3, not number 3, uniform field. Uniform field means what? Same strength and direction at every point must be there. Okay, so when I say uniform field, that means what happened at every point, what happened, it will have the same strength. The same strength means the same magnitude as well as direction at every point in it. In it means inside that what we call the field as uniform field. Clear? Yes. And this uniform field will be represented by parallel arrow lines equidistant from one another. Clear? Yes. Now next, let's try to see electric field intensity. When I say electric field, that is a scalar quantity in one sense, the previous one. When I say electric field intensity, it is a vector quantity. Electric field intensity means the strength of the electric field at that particular point due to that given charge, right? That is known as electric field intensity. Later on in this part, when we go further for higher classes, when we say electric field, we may either mean that scalar electric field of definition, the region or space, or rather this vector quantity, the strength I mean. But when I say electric field intensity, naturally that is what? The vector quantity, the strength. Okay, the force, how what strong the electric field is due to that given charge at that particular point, it will mean the electric field intensity. But generally, we generally say electric field simply just to represent electric field intensity, right? Yes, the electric field intensity due to a charge at a point inside the electric field is defined as a force by a unit positive charge placed at that point. So what is that? The electric field intensity due to a point inside the electric field is defined as the force per unit charge. Got it? Simply like that. But when I say force per unit charge, if you are not able to bring that unit positive charge, suppose instead of bringing that one positive charge, that means unit positive charge, if you bring 5 positive charge, for example, I'm not saying 5 positive coulomb, okay, but 5 positive charge simply. So if that is brought 5 positive charge, the total force in that total force experienced by that 5 positive charge, you divide it by the total number of charge that you brought. That means 5. So total force divided by 5 charge means it will be what? Force per unit charge, right? So mathematically we write it that E vector is equal to F vector by Q naught. So as your force is a vector quantity, your electric field will be also a vector quantity. But when we mean that test charge, okay, then what happened? This test charge must be as small as possible, not only in its size but also in its amount. That is why we take it as unit positive charge. Now when I say electric field in some textbook, you may be found like this, you may find like this, that E, capital E vector is equal to limit of F vector by Q naught when Q naught tends to 0. Got it? Q tends to 0 so as not to disturb the field of the source charge. Suppose if you bring, suppose that Q, suppose Q, a given charge Q is somewhere here and its field is somewhere here like this, for example, and if you bring a charge, what charge? Test charge, of whose magnitude is much more greater than the given charge, naturally what happened? The field for this given charge will be disturbed by that test charge which you brought, of whose magnitude is much greater than the given charge. Have you got it? Yes. Next, uh, it should not be done in that way. Got it? The charge that is brought to test the field of a given charge should not be very large in magnitude as well as in size, but it should be small. So what happened, that test charge must be very much small in size also. At the same time, it must be having the small quantity of charge. In that case, you can write it in this way. That means Q naught tends to 0, right? Why Q naught tends to 0 required? So as not to disturb the field of the source charge. Got it? Yes. Its SI unit is Newton per coulomb. Your force SI unit is Newton, charge coulomb, so Newton per coulomb. And its dimensional formula is what? M L T inverse 3 A inverse. Okay. Yes. A for what? Ampere. Yes. Let's see in the next. Now electric field due to a point charge. Now just to find out electric field due to a point charge, let's take it that this capital P is a point of observation where we want to find electric field due to a given charge Q at the origin, right? So let P be any point inside the electric field of a single point charge Q at the origin as shown in the figure. It is shown in the figure here like this. That means a small charge is placed here at the origin and you want to find out electric field capital E at the point P, okay, of position vector what? R naught. Got it? R naught. That means the position vector from O to P is what? R naught. The magnitude of OP will be equal to R naught and the direction of this position vector will be along this direction OP, right? Yes. So we know that electric field is defined as force per unit charge. Now you try to bring a test charge Q naught at this point of observation P, and then what happened, there will be force of repulsion if these two charges are of like one. If it is positive, then there will be repulsion, and we have to take it that this test charge is mobile, and if there is a force of repulsion between this Q and Q naught, then as it is mobile, then what happened, this can move about. So due to the repulsive force, this test charge Q naught will move along the direction OP, right? So your F vector is drawn along this. So your test charge will experience a force due to this given charge in this direction OP vector, right? Yes. Now then, just to find out that electric field E, we know that force per unit charge. Force means what force? Coulomb's force. Okay, the Coulomb's force experienced by this Q naught, it will be expressed as what? 1 by 4 pi epsilon naught, as it is assumed that the two charges are placed inside the vacuum like that. Got it? Inside the vacuum, or free charges you can say, free space, not charge, free space. So 1 by 4 pi epsilon naught into Q naught divided by R square, right, divided by R naught. So Coulomb's force between these two charges Q and Q naught will be what? 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught Q naught, okay, Q naught divided by R naught square. This is the force experienced by the charge Q naught due to Q, right? Or you can simply say that the force between these two charges, right, divided by Q naught. If another Q naught is here, then Q naught will be cancelled, right? then this q naught and this q naught will cancel and it was as before. Clear? Yes. Let me remove it. Where r is a unit vector, r cap, just to represent a vector quantity. Why? Because your e is also a vector quantity. See, the arrow is there. Okay, so e vector will be equal to what? This 1 by 4 pi epsilon naught q divided by r naught square r cap, where r cap is a unit vector from q to q naught. That means along r naught vector, right? So you can write r cap simply like this, or if you want you can write as r naught. Why? Because I have taken here as r naught, where r naught is a unit vector from q to q naught or along OP, right? Now what are to be noted? Let's see. In the note number 1, if the point charge is positive, then what happen? E will be radially outward. Your electric field intensity will be radially outward. That means if this charge is positive, then it will be radially outward like this. Suppose if your test charge is brought here, then it will be radially outward in along this direction like this. Got it? Yes. If it is negative, then it will be radially inward. If it is negative, for example here, if this is negative charge, this is a positive charge, then there will be force of attraction, right? Unlike charges attract each other. So as this is mobile, this test charge will be directing toward this. Had this given charge is what? Negative, right? Yes. And radially inward for if negative charge, right? Now next, number 2, not number 2. Now if you are going to draw between this E and 1 by r square graph, okay, 1 by r naught here, r naught just to represent distance, so you can simply use r or r naught, doesn't matter. So if you are going to draw a graph between electric field intensity versus what? 1 by r square, then it would have been a straight line like this. Why? Because if you take it here as 1 by r square, then what happened? That 1 by r square and E, they are directly proportional. Got it? Yes. Now, and if you are going to draw without that 1, okay, if you are going to draw electric field intensity with r square is what? In the denominator. So what happened? 1 is in the numerator, on the other side it is denominator. So what happened? They are inversely proportional. So if they are inversely proportional, then electric field intensity will be curved in this way. Got it? In this case, what happened? When 1 by r square increases, your electric field E also increases. When 1 by r square increases from here to here, for example, then what happened? Your electric field will be also increasing from here to here. When 1 by r square increases from here to here, then what happened? Your electric field E also increases from here to here. So we say that when 1 by r square increases, capital E, that means electric field intensity also increases, right? But here, if you are going to draw the graph between E and r square, distance square I mean, then what happened? Your electric field intensity what? Decreases when r square increases. At the very beginning, when r square is very small, electric field E will be very high, somewhere here. Got it? When your this r square increases, then what happened? Your electric field decreases. Got it? Like this, and it will meet in the at the infinity. It will go on decreasing like this when r square increases. Next, let's try to see electric field lines. What is meant by electric field lines? And then next we will see also the properties, some important properties of electric field lines. Now electric field lines, If you want to make a copy, then you can pause this video and you can copy it. Okay, electric field lines, these are imaginary lines. There is no such line when a charge is placed somewhere here, and there will not be any you will not see any lines there. So it is what an imaginary line. It may be straight or curved, and it is drawn along the path followed by a unit positive charge when placed inside the electric field. Okay, when a charge is brought, rather a test charge is brought inside the field, naturally due to either force of attraction or repulsion, the test charge will surely move, right? It may be moving outward or it may be moving toward the given charge. So what happened? These test charge, when we moves along the path, it moves by the test charge. If you happens to draw a curve or a line along the path followed by this test charge, then that line will be known as what? Electric field lines. That is the meaning. Okay, you try to see from here also. Yeah, it can be also defined in terms of tangents also. Got it? Suppose if a field line, I'm sorry. Suppose a charge is here, for example. Got it? This is a given charge, point charge. If it is positive, then what happened? These field lines will be radially outward. Am I right? So it will be radially outward. For example, if it is curved like this, for example, let's say, for this a single point charge, it will not be curved, but if it is far away from here, then it may be curved due to the influence of the other charge. Okay, so let's take it that the graph is curved like this, or rather the not graph, rather the field lines is curved in this manner. Then you can also define these field lines as what? It is a line. Okay, straight or curve, imaginary line, straight or curve. And if you take a point onto this curve, and if you draw a tangent, got it? If you draw a tangent, then this tangent will give you the direction of the electric field due to this given charge. Got it? That is the meaning of this next statement or definition, you can say, of what? Electric field lines. Clear? Yes. Now let's go to the properties of the field lines. Electric field lines are continuous curve but do not form closed loops. Now this is a continuous. When I draw that electric field lines, it will not stop somewhere there as I have drawn. Okay, it is a continuous one. Got it? If you draw somewhere here electric field lines, and if there is a break, and if it start and or continue somewhere here after keeping a gap, it will not be like that. It will be a continuous curve. Okay, but do not form closed loop. It may not be starting from here and it may not come again at the same point. If it is starting from a point and if it comes at that point again, then we call it that as a loop. So in the case of electric field lines, it will not form a closed loop, but in the magnetic field lines, it will form a closed loop. That is the difference, okay, between electric field lines and the magnetic field lines, I mean. So it starts from the positive charge and ends at the negative charge. Got it? Electric field lines will start from the positive charge and it will end at the negative charge. This one, number 2, is already mentioned here in the second definition. The tangent at any point of the field lines gives the direction of electric field intensity at that point. This I have already explained to you. Number 3, no two electric field lines intersect each other. If they intersected, what happened? Then at the point of intersection, there will be two tangents, which will mean two directions of the electric field at a point, okay, at a point due to a given charge, which is impossible. That means is an absurd, because if intersected, we have assumed here now that intersection will not be possible. That is a meaning. So suppose if I draw the field lines intersected like this, for example, at this point of intersection we can draw two tangents, okay, like this, and these two tangent will represent what? The electric field E, right? Here also electric field E. For these electric field lines, this will be the electric field intensity, the direction of electric field intensity. For the second electric field lines, the electric field intensity direction will be along this. But these two electric fields intensity, these are what? Due to a single point charge. Then what happen? At a particular point for a given charge, we can't have two direction of electric field intensity. So what happened? These two field lines never intersect each other. Got it? This may be asked, why no two electric field lines intersect each other? Then the answer will be this one. Okay? Yes. Let's go to the next properties. There are many properties for electric field lines. Let's see. Yes. Number 4. The electric field lines are always normal to the surface of a conductor, but while starting or ending onto the conductor. Suppose if your charge is of the shape of like this, say for example, if your charge body is in this shape, got it? And if it is positive charge like this surface is somewhat slanting to its length. So what happen? Electric field lines will not start like this straight, not like this. Rather, electric field lines will be starting perpendicular to this surface. So your electric field lines will be what? Perpendicular. Got it? So what is said? Your electric field lines are always normal, perpendicular, normal to the surface of a conductor, but while starting or while entering. If it is negative, then electric field lines will end at the negative terminal. So when it comes, what happens? If it is negative, then electric field lines will be also perpendicular to the surface. And if it is X, the reason. Therefore, what happened? There is no component of electric field intensity parallel to the surface of the conductor. Because what happened? When this electric field line is coming out perpendicular, then there will not be no component of electric field lines parallel to this surface. That is the meaning. Got it? If it comes out like this, then what happened? We can resolve it into two rectangular components, one along here. Suppose if this is not the one, if this electric field is there, for example, if this field is there, this one is not there. Got it? If electric field is like this, which is not perpendicular to the surface, if electric field is like this, then what happened? This electric field can be resolved into two rectangular components, one along the surface of the conductor, another perpendicular to it, right? In that case, what happened? This component will be there. What is this component? Component parallel to the surface of the conductor, right? But as electric field lines comes out perpendicular to the surface, this component will not be there. Got it? Component parallel to the surface will not be there. And if you are asked why such electric field lines comes out or comes in perpendicular to the surface, then you have to say that as there is no component of electric field parallel to the surface of the conductor, so what happened? Your electric field lines comes out perpendicular to the surface, right? Yes. Number 5. The number of field lines per unit cross-sectional area perpendicular to the surface is proportional to the magnitude of electric field intensity. This is very important, right? And this will be used when we come to that of what the strong, just to find out that strong electric field or weak electric field, this will be used. What is that? The number of what? Field lines per unit cross-sectional area perpendicular to the surface is proportional to the magnitude of electric field intensity. Suppose whether, if you want to find out whether the electric field intensity is strong or weak, when we want to see that, then we need to find out these whether its density of electric field lines is large or small. You need to see, for example, if this is a point charge, then what happened from this point charge, a small point charge, let me draw in a circle like this just to represent a sphere. So what happened, your electric field lines will be coming out like this in all directions. Got it? In this manner. So I will not draw all those arrows, okay, but you think that it is coming outward like this, right? Suppose in a particular there will be many field lines. So when you carefully observe the field lines, what happened, somewhere here near the charge, the number of field lines passing through a definite given area, okay, and somewhere here with the same area, what happened, the number of field line passing through this area, same area at this point and somewhat closer to the charge, this field somewhere here, the field lines, the number of field lines is more here than here, right? So this region where the number of field lines passing through a given area perpendicular to it, if it is more, then this region is having what, stronger field than the one which is having what, lesser field lines passing through the same area. Got it? Yes, that is the meaning. Now next, number 6, right? Electric field lines contract lengthwise on account of attraction between unlike charges. We know that unlike charges attract each other. Like charges repel what? One another, right? Or each other, you can say. Yes, this is of only two, between two charges, right? Now, why these electric field lines contract? It is because what? Unlike charges attract each other. Suppose if there is a positive charge here and here it is negative charge. I should not draw in a very lengthy way like that. So negative charge here. What is wrong? Negative charge here like this. So what happened, your field lines will start from the positive charge and toward the negative charge, okay, like this. So this will be the field direction. But if you want to start from here, then the field lines will be curved like this, right? Field lines will be curved like this, in this manner. Got it? Like this. Clear? But if I haven't intersected, then it should not be intersected, okay? But let's assume it in that way. Now when you see here like this, another field lines, it will be moving in this way, in the same way, right? So what happened, lengthwise it contracts, means what happened, it comes closer and closer to what, its length. See, when you come closer and closer, somewhere here it is contracted lengthwise, the head and the tail, okay, you can take it in that way. These come closer and closer, so we say that it contract lengthwise. Got it? This represents what, or this is due to what, the unlike charges attract each other. But in the case of this number 7, what happened, they have lateral pressure. Lateral means sidewise, okay? So what happened, sidewise they will repel each other, one another. So that represents what? That represents unlike charges, like charges repel each other. Now what is that meaning? Let me show you here in this diagram. What happened, these field lines, one field lines, another field lines, another field lines, there is a lateral pressure in between these two. Lateral means sidewise, okay? This side and this side seems to be repelled, Had there been no repulsion, then this would have been closer, no? But it is not so. Somewhere here it will be closer, somewhere here it will be farther away, like that. If you happens to draw that one fill line from somewhere here, then it will be curved more upward like this, in this way. Had it been drawn again, then it would have been in this direction. Got it? So there is a lateral pressure, sidewise pressure, okay, one another between the electric field lines. So that is also one of the property, and this lateral pressure is due to what? The like charges, yes, like charges repel each other, right? Yes. I think there are some more. Yes. Yes. Next number 7, right? Yes. Number 8. Electric field lines do not pass through a conductor. So what happened? Electric field lines do not pass through a conductor because the interior of a conductor is free from the influence of the electric field. What happened? Whenever there is a big conductor of thickness, say finite thickness, then what happened? These electric field lines will not pass inside the conductor. Suppose if you are having a shell, spherical shell, metal conductor shell, then electric field from outside will not penetrate through those conductor. That is the case for where we can have that electro shielding. Okay, electro shielding is just like that. Suppose I will give you one example. We usually say that whenever lightning is there, then we usually say that to be inside the car is much safer than to stand beneath what? A big tree, right? Because near that big tree, what happened, as during the rainy season or rainy days, what happened, electric discharge may take place through that tree, and that lightning may be coming down, that means current may be coming down through that tree toward the earth. Okay, and if you are standing near the tree, then you may get shocked. But if you are inside a car, then what happened, even though that lightning strikes onto that car, you are safe, you will not get any shock. Why? Because that electric field cannot enter inside a conductor, because your car is a conductor. The upper part of the car, the roof of the car, these are all conductors, so that conductor will not allow to penetrate inside. Through that conductor, electric field will not allow to penetrate through that conductor, so you are safe. Got it? It is of that one. Number 9, last property. Electric field lines are allowed to pass through a non-conductor or dielectrics. But in the case of insulator, what happened? Like non-conductor means insulator, okay? So electric field lines are allowed to pass through them. And this dielectric, it is a different or special type of insulator where electric polarization can take place when such insulator is placed inside the field. So that material we call it as dielectrics. I'm repeating again, dielectric means what? It is an insulator which can produce polarization when it is placed inside the electric field. Now I will tell you about that polarization later on when we are dealing with about with that of capacitor. Okay, yes. Now electric dipole. Electric dipole means what? Di means two, pole means polarity, that means negative pole, positive pole, we generally say like that. Okay, yes. So electric dipole is nothing, it is a system of two equal and opposite charges separated by a small distance constitute what we call as an electric dipole. I will not read like this, okay? Instead of that, let me explain you so that it will not take much time, okay? Now, two equal and opposite point charges separated by a small distance represents what? An electric dipole. It is also all given here. Generally, we take it that the middle point of this dipole as O. This is a matter of notation only. You can represent by another symbol also, no doubt. And the length between this negative charge and positive charge, we generally write by twice L, so that half of the dipole length will be represented by L. L, total length, is denoted by twice L. Got it? Yes. Total charge of an electric dipole is 0, but its electric field is not 0. Total charge 0 means what? Minus Q plus of this plus Q means what? It will neutralize. Total charge is 0, but their electric field is not 0. But there are some reason electric field will be 0. We can find it out, no doubt. But generally outside it, there is no electric field 0 due to this what? Electric dipole. And that means some finite value are there, okay? Some finite value of electric field are there even though the total charge is 0. That is the meaning. Now let's go to the dipole moment. Dipole moment is nothing but this is a strength of that electric dipole. Got it? Strength of an electric dipole, we call it that as dipole moment, and it is expressed as what? Either of the magnitude of the charge of the two charge. I mean, if you want to take it this minus Q, magnitude means Q. If you want to take magnitude of this, it will be plus Q, because they are of same magnitude, just opposite in nature. So two equal and opposite, I have to say like that, two equal and opposite separated by a small distance constitute what we call as an electric dipole, right? In that way, what happen? Your dipole moment maybe will be measured by the product of the magnitude of either of the charge and their dipole length. We call it this twice L, distance between the two charges, we call it as dipole length. So twice L times Q, that will give you the strength of the dipole moment. You know, dipole moment is a vector quantity, that's why we generally write by P vector. So if it is a vector quantity, then it will have to have its direction, right? The magnitude will be given by the product of this. We generally say twice QL, dipole length times the charge, okay? Twice QL, and the direction will be from negative charge to positive charge. So that is what I am writing here, that P vector, it is denoted by small p vector, okay? That is what I am writing here. So your small p vector will be directing from where to where? From minus Q to plus Q. That is what I have drawn here, right? So this is the direction of the dipole moment. Now each SI unit, that means dipole moment, SI unit of dipole moment will be what? Charge is coulomb. SI unit of charge is coulomb. SI unit of length is meter, so coulomb meter. And its dimension is what? M0, L1, T1, A1. Okay, no need of saying all those ones, so you can write M0, LTA. Now if Q increases, if the magnitude of Q increases, keep on increasing, and if this dipole length keep on decreasing, that is the meaning here. If Q increases and twice L tends to 0, that means if keep on decreasing, okay, such that what happen? Your dipole moment, the magnitude of dipole moment remains constant. then such condition of an electric dipole, we call it that condition or that situation as an ideal dipole. So what is an ideal dipole? An ideal dipole is a dipole in which Q increases and dipole length decreases such that decreases to what? Tends to zero. Okay, so decreases that the magnitude of the dipole moment remains constant. Thus, an ideal dipole is the smallest dipole. Okay, and its size will not be so large, but we can say that it is of no size, as if that this point minus q and plus q, they are residing at the same point. Got it? It is not at the same point, but as the distance is very very small, to some fair approximation we can assume that they are residing almost at the same point, right? That's all for today, and in the next class we will try to see about the electric field intensity due to an electric dipole. Okay, let's stop it here.